All right, shall we start? So we'll do the second half today of color. So we'll kind of switch to practical applications of color. And we'll talk first about cylindrical color systems used by artists and Photoshop. And then we'll talk about chromaticity diagrams, which is a way to talk about the color without the brightness. And we'll show two applications of that: white balancing in photography and gamut mapping. And both are applicable to photography. Just a reminder on the assignment let's see. Is there another mic here that might be on? No, that's off. There's I forgot to put up the assignment, the landscape assignment, but it is up now. And so there it is right there, landscape assignment. So that's up for those of you doing the assignments. All right, just a reminder. So today we're doing color. There'll be only one lecture next week on Monday, and then two lectures the following week on light and reflection and lighting for photography. Okay. So let's get on with this. All right, so let's talk first. There's definitely an echo.
No idea where from. I think the mic is just hotter than it's normally been.
Okay. Something I should do here?
The mic's pretty far away from your mouth.
I can work on that. It might be better or worse. Should be better. Yeah, should be better. Because you ought to be able to turn it down. Or I ought to be able to turn it down. Okay, so something needs to be turned down. Well, I can turn down the gain here. Does that help? That probably, I bet that helps. I just turned down the gain.
There's another receiver down there.
Right. At least I think I turned down the gain. I don't know if I actually did. Am I even broadcasting now? You ought to make sure I'm broadcasting. All right. So let me go to one of the applets. And so we've talked about, I've shown you this applet before. And so on this applet, there's the 3D color space. There are the axes for a particular set of primaries. And one thing I didn't show you is this scaling here. So what that scaling means is that we can set some arbitrary sliders on the strength of the red, green, and blue primary. And so inside any old television set, there would be these dials you're not supposed to fiddle with that do that. And we can think about that as setting the color of a reference white, which would have unit amounts of that red, green, and blue subject to this extra scaling. And by changing that scaling, you can decide whether you want that reference white to be bluer or redder or whatever. So go back to the slides. So choose three primaries, whether they're pure wavelengths or not, and then adjust the scaling to the nominal 255, 255, 255, so that you get some white that you like. And it could be a bluish white or a reddish white, and that's called the reference white. And then once you've set the primaries and the reference white, now here is a color space that you could manipulate. Computer graphics people know how to find colors in this space. But artists don't like this space. This isn't a logical space for them. So what are reasonable color spaces for artists? So over the history of art, people have theorized different ways to organize the colors. And for the longest time, really until Newton, they always put them on a linear scale. And one of the reasons they put them on the linear scale was they were stuck on the idea that white and black should be in this organization of colors. And black is very dark and white is light, and so they would try to organize the colors by brightness. So here's a typical one from the Baroque era, Peter Paul Rubens. The ancients also had a linear organization. Newton was the first who said, wait, if we remove black and white, then we can actually also close the circle, add a little bit of purple, and it makes a very nice circle. And that is a convenient way to look at color, and actually has some basis in human perception. So here is this line of what we'll later call extra spectral purples by adding red at one end of the rainbow to blue at the other end of the rainbow. All right, so that begins to give a good start to a way that artists might think about color that's a little bit more intuitive. So we can start with a circle like that, and we can put, if we'd like, let's say red and green and blue, and if we want to get pedantic, we can draw triangles and call them magic triangles in some way. We could also put the secondary colors here, yellow and cyan and magenta, although they aren't necessarily the broadband. We're not talking about that. We're just talking about the human perception. And so this is a circular scale, and we'll call that a good way to determine hue, or to denote hue. All right, so there are other aspects to color. And another one would be a saturation scale. And we might put neutral here, and although an artist wouldn't say this, a pure spectral color. Let's call that pure spectral color here. And so this is a closed-ended linear scale for saturation. And an artist would understand that notion of more grayish or blackish or whitish versus more fully saturated colors. There's got to be one more variable in the way an artist would think about this, and that's how light or dark the color is. So here we actually have a bit of a dilemma. So this is saturation. We can talk about lightness, but there are two ways we could talk about lightness. We could talk about an open-ended brightness scale for a luminous object, where this is dark and this is brighter. Or we could talk about a closed-ended scale for a reflective object. And we might call that whiteness, where this would be 0% reflective, and this might be 100% reflective. So whether we take closed-ended or open-ended, what we have here is three variables: hue, saturation, and lightness, one of which is circular and two of which are linear scales. So that should immediately suggest what kind of coordinate system for this three-dimensional space. Cylindrical coordinate system, where you have an axis in the middle, and then you have some distance out. So there's a theta here, and move the word hue over here. So theta, and then a distance out along that theta, and that would be r, and a height here, and that would be y. And that would be the same as the hue, the saturation, and the lightness. Okay? And then if we'd like to, we could talk about equal surfaces, just to get you a little bit more comfortable with this. So we could talk about an equal hue varying saturation and lightness surface. So that might be something like this. See what I'm drawing there? That would be an equal hue, or constant hue. Or I could draw an equal saturation surface. So can you think of what that will look like? That'll be something like this, a peel of the onion. Or an equal lightness, which would be some layer. And all of that would make a fair amount of sense, and you could imagine displaying those as selectors to an artist. So here is exactly that cylinder. Hue around the outside, saturation as a radius, and lightness as you go up. It's not a great representation, though, because it's all white at the top and it's all black at the bottom, and so you're kind of wasting real estate in this representation. So could you pinch in the top and pinch in the bottom? Well, sure, because it's an arbitrary transformation on this three-dimensional color space, just some math. And so here's another representation of the same. It's still a cylindrical coordinate system, but we've applied an additional transformation to pinch that in. And that's called the HSL double cone. So that solves the problem of not having too much white and too much black. But when artists mix, let's say, light, red, green, and blue lights, they're doing stage design. When they add red, green, and blue, they'll get white. But it's a little strange here because at the same plane that they have the red, green, and blue is a gray. The white's kind of up here. So the lighting designer would say, push that white down. Okay. Another transformation, which is still a cylindrical coordinate system. Now white is on the same plane. But the artists, they will say, oh, but it should be black in the middle, not white. Right? Because if I take red, green, and blue paint, I'll get black. But you can easily do the same thing. That's just another transformation. Squish the bottom up instead of squishing the top down. So these are all reasonable transformations of the same basic cylindrical coordinate system. And you can find these in one way or another on a variety of programs as color pickers. Let's just look at one of them. Let's look at that one, which is Photoshop. So Photoshop's system has, let's see, it's got this two-dimensional thingy here and this one-dimensional thingy here. And so if we look at our coordinate system, we can see, let's see, that is really exactly this. It's a constant hue surface with increasing saturation and decreasing brightness. It's white along the top. It's got white and the pure hue along the top, and then it's got black at the bottoms, right. And then it has a ring around the outside. And that ring is this thing here. So that's enough to choose three-dimensional colors. So actually, if you look at the, there's brightness, saturation, and hue. If you actually look at the math, so you can find web pages on this stuff. It's a Cartesian to cylindrical coordinate system conversion, and it's actually, where's my cursor? There we are. This system is basically this system here, with white and the saturated colors on the same plane. This one that I described here had all white at the top and all white at the bottom, so it was closer to this system here. But again, they're all just simple transformations of one another that are still cylindrical systems. You could argue that, well, instead of doing black at the bottom, they should have pinched it in and just done a triangle. They didn't need that. Then it would have been more like the cone that we talked about, the single cone. but maybe it would have been a little bit less intuitive or harder to display, so they didn't bother doing that. There's other interesting stuff here. They have a conversion between RGB and CMYK. This depends on the choice of primaries, exactly what that conversion will be. You can think of it as sort of roughly 1 minus RGB, but it's not exactly. It depends on the primaries. And there's a K in there as well. The K is the black extra primary. And then there's LAB, which I'll talk about later in the lecture. That's an equal perceptual space. We'll come back to that. Okay, so we've talked about artist's system that has hue, saturation, and lightness, which is a circular and 2 linear scales, makes a cylindrical system, and then you can build selectors based on that. So any questions about this? Because that's all I'm going to say about these artist cylindrical systems.
Do people just use brightness and lightness interchangeably, or is there some technical nuance?
They use it interchangeably and don't understand the technical nuance. There's no formal definition of any of those. I pulled them out separately so that you could think about reflectance versus luminance.
One of them is 0 to 100 in the opposite direction of the 0 to 255. I don't know where that comes from. But
Okay, some arbitrary scaled
you will see that,
0 to 100 or 0 to 255.
and that one has black at 0, another has white at 0.
Right. People have invented scales. I don't think there's any universal standard. I've never seen an international standard on this. All right, nothing on the dory, so let's keep going. So let's talk about chromaticity diagrams. So there's the RGB cube that we've talked about. Points in the RGB cube having the same chromaticity, meaning the same coloredness, but varying brightnesses, lie along lines emanating out from black, right? So you can go from black to white and it'll just get brighter, or any other radial out from black will have the same coloredness, it'll just get brighter. And so here's another way to think about that. Here's the black, here's the white, this just gets brighter. Along any of these lines it gets brighter. So it's a reasonable thing to think about removing that brightness and just talking about the color by itself, because that has the advantage of reducing it to a 2-dimensional coordinate system. In the same way that if we took out lightness here, it's a 2-dimensional coordinate system, but let's stick to these Cartesian ones. Okay, so there's black, there's white. The way to do that then is to project any point you're interested in talking about onto some plane, and just choose a plane in the middle of that cube. And you're projecting it back toward the origin and finding its intersection with that plane, and that will factor out the brightness. And so by convention, the diagonal of the cube is taken, and there's the projection. That's what that looks like. And once you have projected all points onto this triangle in the middle of the RGB cube, then you can talk about it using 2 axes instead of 3. And the 2 axes could, for example, be this and that edge of the triangle. And so that is what's done. The projection that I just showed you is exactly those equations. And I can show you that geometrically with a flash demo. So here's an applet. There's the same spectral locus we're used to looking at, and they're the matching functions. We've chosen a particular set of primaries. So everything I'm saying here is for a particular set of primaries. So I'm going to show you something called the chromaticity diagram for a particular set of primaries. And ready for the magic? Watch this. Isn't this a cool flash animation? They're projecting it. It's being projected onto the locus. Let me show that again, just because it's so cool. So everything's being projected back toward the origin until it intersects that triangle. And then we can align it so that those axes that form the edges of the triangle R and G are upright. That is now a chromaticity diagram with coordinates small r and small g. And brightness has been factored out. So let's go back to the So there's the diagram. There's R and there's G. It's for a particular set of primaries. Mixtures of colors do lie along straight lines within this chromaticity diagram. It's still the same linear space, or a transform of that linear space. There's the neutral point. That's the diagonal through the cube that went from black to white. It's at 1/3, 1/3, it's at 1/3, 1/3. But there's some problems with this as a common way of being able to talk to people about color. First of all, it did depend on the primaries that we chose. So if we choose different primaries, we'll get a different chromaticity diagram. The spectral locus will be in a different place. The other problem is the spectral locus is not inside the triangle. It's got some negative numbers in it, which is kind of peculiar. And so primarily for those two reasons, it's not a great system. But the same construction could be performed with any set of primaries, meaning any set of 3 vectors in the original rho gamma beta space. So let's think about that for a second. Here's the rho gamma beta space. And the locus of spectral colors is this curve in 3-dimensional space that looks like that. And if we choose any particular set of 3 primaries, then we're choosing some vector like this that is inside the all-positive octant of rho gamma beta, because it is a physically realizable color. Let's say it's a pure color like this. But you can see that the spectral locus falls outside that. And so any scaling of this that would make an RGB cube, where these are R, G, and B, the spectral locus bows outside of that, as it does on that diagram. Okay, so suppose we were to take that red, green, and blue primaries and just kind of go like that, and just open them up. It's a reasonable transformation of a 3-dimensional space, and we could open them up enough so that the spectral locus would be entirely inside the all-positive octant of the new primaries. So I know I'm kind of ripping your head off here, but let's define a new, let's take this one and we'll swing it out to something like this, so that the curve is entirely inside. And we'll call that X. And then we'll take this one and we'll kind of push it down into the board. Kind of hard for me to draw here, 2 dimensions. Here, let's do it this way. And we'll call that Y. So there are an infinite number of possible choices on that, on exactly what that is. And then we'll do the same thing here. We'll take the blue and we'll kind of expand it out, and we'll call that Z. So those are not physically realizable primaries. You cannot make a light of that color that we would see. It doesn't fall within the all-positive octant of rho gamma beta, which is our visual system. But it's mathematically possible from this diagram. All you need to do is define new matching functions. And that's exactly, let's go back to the applet. That's exactly what this is over here. So here's X and Y and Z, and here's what the spectral locus looks like in that space. So they're matching functions. So here are the matching functions for a particular set of RGB. Here are the matching functions for X, Y, and Z. They are all positive. The spectral locus does not bow outside of them. If you could make those primaries physically, then you would not need those phantom 3 knobs in Maxwell's matching experiment, except that you cannot make those primaries. It's just a mathematical abstraction. But it's got this nice property, that there's no bowing. The all positive octant completely contains that spectral locus. We can do the same projection onto the triangle in the middle of that XYZ space. That's what it looks like. And then we can have a little x, little y, which is now a new chromaticity diagram in which the spectral locus sits inside the triangle. I know this kind of rips your head off, but it is exactly what is done as a standard way of talking about color. So the Comité International d'Éclairage has defined this set of primaries in terms of these matching functions such that little x, little y after the same projection does enclose the spectral locus, and there is the spectral locus now. And in fact, with the whole spectral locus inside, it makes sense to connect the red and blue ends with what's called the line of extraspectral purples. Extraspectral because they do not appear in the rainbow. And that begins to look a lot like Newton's color circle, doesn't it? So it's a very convenient way to talk about the color of things. And it's standard. So it doesn't depend on the choice of primaries. Okay. Make sure I covered everything. Yeah. All right. So that's enough now. That let's consider an application in photography. And the application we'll talk about is white balancing. And this is a convenient space in which to talk about white balancing. So there's X along the bottom, Y. You can sort of think as X as being kind of in the reddish part of the spectrum and Y is sort of in the greenish, just from this diagram here, but it's not exactly. And here's the locus of spectral colors. There's the line of extraspectral purples. And the apparent colors emitted by a black body radiator, meaning a material that absorbs all light that strikes it, but that emits light when heated to incandescence, falls along a line. So this should actually be a very familiar line to you. You look at embers in a fireplace, and if they're not too hot, they'll be reddish, and then they'll be yellowish, and then they can be white hot. So we kind of intuitively understand that scale. And they even might get a little bit bluish white at the end. So that's the color temperature scale. So not all light sources that we would deal with in photography lie along this line, because we're not always illuminating things by bodies heated to incandescence. So we talk instead about a correlated color temperature. And a correlated color temperature means, well, we find a point somewhere on this curve that looks like it. It isn't necessarily a perpendicular drop to that curve. It's a nearest point in some other space. But you can just think about it as some close point is called the correlated color temperature. And so here are the correlated color temperatures for some common light sources. This might be close to a black body radiator, might actually sit on the curve, but the other ones don't. But here are their correlated color temperatures. Okay, so this one's special, D65. We'll talk about that in a moment. All right, so white balancing in photography. The premise is that an object is illuminated by colored light, but it should not be presented back to the user. So if it's illuminated by colored light, it's going to take on some color cast. And the premise is that we don't want to display it back to the observer of a photograph that way, because they didn't see the light source. So they can't mentally compensate for the fact that it was illuminated by a colored light. And so they can't compensate for the strong coloring. That's the purpose of white balancing, is to estimate the color of the illumination and shift the colors in the photograph so that the user can look at it and imagine that it was illuminated by some standard color. So choose an object in the photograph that you think is neutral, is the basic principle, reflects all wavelengths equally, and compute scale factors that forces that particular object's RGB to be neutral. And that will be a set of ratios you then apply to all the pixels in the image. So as an example, this. Suppose that the object you choose had RGB 140, 120, 100. So this object is kind of reddish RGB. If you claim that it was a neutral object, meaning an object that reflected all wavelengths equally, it's probably true then that the light was reddish. So then you come up with scaling factors, 120 over 140, 1, and 120 over 100. And you apply that to every pixel in the image. So those scaling factors will then obviously increase the blueness and decrease the redness to compensate for that. And that's basically what white balancing is. So your computer's interpretation of the final scaled values depend on the color space of the camera. So the color space of most cameras is sRGB. We'll talk about color spaces a little bit later. And the reference white for sRGB is this D65 that I mentioned before, this correlated color temperature for a black body heated to 6,500 degrees Kelvin. So the standard white balancing then will shift the colors back as if it were illuminated by D6500, which is a slightly bluish daylight color. So white balancing on an sRGB camera forces your chosen object to appear this bluish white. When we walk by, when we're outdoors and we walk by and we see someone has a television set inside, it always appears a little bit bluish. That's because this D65 is slightly on the bluish side. So if you trust your object to be neutral, this is equivalent, as I said, to finding the color temperature of the illumination. So now the question is, how do you estimate those scale factors? How do you find a neutral object in the scene? It's not easy. So here are some possible methods you can imagine. Gray world is kind of the standard first order attempt to solve this, which is you just take the average color of the entire scene, you assume it ought to be gray, and you compute a scale factor from that. So I've deliberately chosen a scene where that's probably not a good idea, just to show you what it does. So here is the actual average color of that scene. If we force it to be gray, then, so here is the actual average, and we're forcing it to be gray, so we're applying those scale factors, and here's the image that will result. It's not horrible, but I don't prefer it. So failure mode number one is the scene is not gray, and we assumed it was gray. But failure mode number two is that the user might not want full compensation. And you have to think about those two separately. So snow should arguably not look like this. It should probably be white. So this is a failure of white balance. But I actually want my sunsets to be kind of red. I don't want it fully moved back to that previous image that you saw. This is scene dependent. Suddenly white balancing looks a little bit more complicated. It's kind of semantically dependent. You might want a learning-based auto white balance algorithm. You might. All right, so here's another possible way if you don't like just averaging all the pixels in the scene. Assume that the brightest pixel in the scene after the demosaicing is a specular highlight, meaning a shiny spot, and assume that that reflects all wavelengths equally, and therefore it ought to be the same color as the light source. What do you think about that as a algorithm. Don't like it. How's it going to break?
Anything that's clipped in the scene is going to trip it.
Anything that's clipped in the scene, all right? So the red, green, and blue got clipped, all right? How else might it fail?
Specular highlights can still be colored, right? Like if it's like a red chrome on a car, that kind of thing.
Very good. Specular highlights could be colored. A metal, like the gold that I showed in the Dutch still lifes, could absolutely be colored, yeah. Could also fail if you were looking at the light source. And the light source was colored. So fails if the pixel is the light source, fails if it's saturated, fails if it's metallic. So I think we've gotten, fails if the brightest is actually not a specular highlight, but is something else. So there are lots of ways that this fails. So another algorithm might be find a neutral colored object in the scene, which is kind of where we started this. So how do you find a neutral colored object in the scene? Well, you go to the patent literature and you look for Nikon's patents on it, and this is hard. And so this is exactly why learning seems to be a good approach for this. Lots of training data.
Bring a neutral colored object and place it in the scene.
Or, yes, or take a known neutral colored object and put it in the scene, like a Macbeth color checker chart, and actually take a second shot of your scene if you can with that in it. Yeah, there are lots of ways of doing that.
Don't all photographers always shoot with a Macbeth color checker chart in every image?
Keep one in my lens cap. Yeah, that's a kind of a standard solution, actually. I'm not kidding. Keep some reference source in my lens cap and just stick it in the scene. You can also manually specify the white balance on most cameras. I didn't bring my SLR with me today, but there's a manual white balance adjuster. And so the way that would be done is for a given camera, you can measure the RGB values that will come off the sensor when any known neutral object is illuminated by a particular illuminant. And then from that, you can compute scale factors. And so that's how the camera can apply white balancing if you select one of these illuminants on the menu for the camera. So, for example, if you choose daylight, daylight is a slightly warmer color temperature, lower at Kelvin actually. So when I say warmer, I mean red, more reddish, than the D6500. And so it will think that the entire scene was illuminated with a slightly redder than desired light source, and so it's going to boost the blues. So if we do that incorrectly to a scene that was well white balanced, we can create this bluish scene. Or if I had set the white balance when I shot this to, say, tungsten, which is very low Kelvin, very warm, then it will say, oh my gosh, illumination must be so red, I'm going to boost the blues a lot. And so you can get an incorrectly white balanced scene like this. Okay, so choose 3 primaries and reference white. You get an RGB cube. We talked about the projection to make the chromaticity diagram. We talked about the standard primaries and their standard chromaticity diagram. And then we talked about white balancing and correlated color temperature. Any incandescent questions?
So why do photographers use this Macbeth card instead of a gray card?
Oh, right. Yeah, that's actually correct. They should only need a gray card. And actually, that's what a lot of photographers carry around in their lens cap, is just a gray card.
So what is the point of the
They shouldn't need it if their camera's already calibrated.
less of a thing in digital? In film, you actually checked, when you were running the process, you checked multiple points.
So Zalman says that in film processing, you would want to check multiple points along the spectrum, but in digital, you shouldn't need to. In digital, you're right. Assuming that the camera has been calibrated at the factory, you should only need a neutral object.
You can pull a full profile from the chart if you want to. But
If the wrong color correction has been applied, you will only know it if you actually have the reference colors.
If the wrong color correction has been applied, you'll only know it if you... Oh, you mean if you already have the image?
If you have the image that's been properly white balanced, but with the wrong color correction profile, it will look off.
Oh, with the wrong color profile. Yeah. Right. So then that's...
wrong is an interesting term, right? Because the camera chose some particular interpretation, which might not like it's necessarily a bug, it just might not be what you wanted.
Let's not rat hole on this. Okay.
Mark, I had one question
Yeah.
about the terminology of warm versus cool. I've always wondered, is this a function of English, or is there some other background behind the fact that we call warmer things?
Well, ice is blue and fire is red. Maybe that's where it comes from.
But we know that white hot is hotter.
Yeah, but white hot is bluer than, yes, yeah, I can't defend the English language.
Is that English, or does that hold against other languages?
Don't know the answer to that.
White hot wasn't that common when it was made.
Yeah, so the suggestion is that white hot was actually not, a relatively recent development in human history. Be able to look at white hot objects.
There's in art, warm colors and cool colors are an emotional, like when they teach you how to paint and whatever, they actually present this. I don't
Right.
think it's solely a function of English.
Yeah, and I think it's probably the fact that snow was kind of bluish and whitish, and that fire was all in the yellows and reds, and so that became a spectrum that was used. All right. Any other questions?
Do people use chromaticity diagrams for things other than color temperature?
They absolutely do. I will show you some more applications of chromaticity diagrams in just a moment. Yep. As a matter of fact, application of chromaticity diagram number 2. Color standards and gamut mapping. Okay, so the chromaticities fill a triangle in the XYZ diagram, different triangle for each choice of primaries. This is called the device gamut, is what that particular reproduction device can do. And here are a number of gamuts here. So why is this diagram, which I scanned from a book, black outside of this one gamut called the printer gamut? Well, they don't have the gamut to make it in the book. Right. A slightly harder question. Why is it a funny shape? It isn't a triangle. It seems to have, let's see, 1, 2, 3, 4, 5, and there's one hidden behind there. It's got 6 points on it. Why does it have 6 points? There's someone besides Solid. No, there probably aren't 6 inks. All right, Florian.
So it's a rotated and distorted cube. You're looking at it sort of diagonally.
That's one way to describe it. It's a rotated cube, the RGB cube. Another way to think about it is the method of printing that I said. Remember, you mix the cyan, magenta, yellow inks, you get RGB, which then makes all 6 points of the cube. So it's the same as the answer that Florian just gave. And we're looking at all 6 points of that cube, or we're looking at those extra primaries that are then governed by the Neugebauer equations that I talked about last time. Okay, so XYZ is a standard way to talk about things. So if you go to a website like this that is a Pigment catalog, and let's pick out Prussian Blue, and it'll talk about Prussian Blue, and you can buy it. And here are the XYZ coordinates right here. So it is a standard way to do it. If they're talking about RGB, then they've got some set of primaries they've chosen for that. But the standard way to do it is to talk about XYZ. Excuse me. So you guys know about the Color Marketing Group. This is an organization that people don't generally want to admit exists, that chooses your colors from year to year. They're in New York, and they gauge the mood of the nation or of the world. I don't know what they'll do in an election year like this. And they'll come up with a palette. And they'll publish that palette, but they'll sell for a lot of money the actual XYZ coordinates of the colors in that palette. So that you could, for example, get a car and a suit that match. Or bridal registries kind of depend on this Color Marketing Group so that you could go buy dishes and tablecloths and so on that all match. Probably a little bit out of date. But yeah, this group exists, and they charge a lot of money for these colors. So if you notice that everything happens to be sort of like, what is it, tangerine and lime this year, strange colors of VW bugs and Teslas, it's this Color Marketing Group at work. Right. Yeah, it's not an accident. Okay, so let me talk about Hanna-Barbera Productions. So in a previous life, I worked on computer-assisted cartoon animation, and we were automating their cartoon animation process. And so in order to do that, we had to get the colors right. And so I went into the paint lab at Hanna-Barbera. Does anyone recognize any of these things? Yeah, okay. All right. Scooby-Doo, at least. And I went into their lab, and they showed me their magic ring of reference colors of 125 different colors. And then I had to reproduce those accurately inside the computer. Okay, so how do you do that? Well, let's see. Take those physical color samples, you send them off to a laboratory, and they will run them through a spectroreflectometer, which looks a little bit like this, except instead of a light source here, there'll be the sample illuminated by some reference illumination, goes through a slit, and then they sense how much of each wavelength. They move this slit around, and they'll determine how much of each wavelength exists, and they'll come up with a spectrum. So once they come up with a spectrum for each color, they'll then run it through those X, Y, Z matching functions that are the standard, which is exactly, you've seen these before, except you saw red, r, little g, and little b here, instead of X, Y, and Z, and come up with a single set of coordinates. And that's what they sent back to me. So I had to know my color theory in order to do this. So they send back X, Y, Z. I could then factor out the brightness if I wanted to and just get little x and little y. And then, so there are the same projection equations that I showed you that project all the points onto the triangle that's halfway through the XYZ cube in this case. And then I could look at the colors for Fred Flintstone. And I could plot them on this XYZ diagram, and I could compare them, for example, to the National Television Standards gamut, which is the colors that it is possible or legal to transmit. And lo and behold, it turned out that Fred's necktie was out of gamut. It was there. So how did this ever work? So the way they had done it before the computer was they had made a film with their animation cameras, sent the film off to NBC Studios, or it was ABC, and then something happened inside the studio so that they didn't get a $1 million fine for broadcasting something illegal that might have interfered with adjacent channels the way these colors are modulated. And so I went to the engineers at the studio, at the television studio, and I said, "What do you do about this?" And he just went over and showed me a knob on his analog controls and said, "I just did this." And I said, "What rendering intent of gamut mapping is that closest to?" And he looked at me like I was some kind of smart ass. We'll talk about those rendering intents and gamut mapping in a moment. I kind of knew he wasn't going to give me an answer for that. He's just moving some analog knob that would take everything and move it inward a little bit toward the neutral point. And I was being a little bit of a smarty. All right, so let's talk about that. Suppose you actually want to fix that problem. What would you do? So you're in control of a computer system now. Someone besides the ringers in the class? What should we do with that color? Yeah.
Okay, you should scale the triangle to, make that.
Well, you can't move the triangle. The triangle are the primaries.
You scale the colors
Oh, scale all the colors.
so that they fit.
So,
The colors you want fit inside the triangle.
so for example, you might take this color and then move it let me use my cursor here. Move it perpendicular to that outer line till it lands here. Is that what you want?
Well, somehow squash the entire space that you have.
Oh, squash the entire space down to the origin, or what?
So that the colors of interest fit.
Oh, fit. Okay. So maybe you'll squash them toward that point. Will you squash them all linearly, or will you squash them proportionately?
What would I do?
Right.
I would squash it so that the colors of interest, like you do the least distortion to the space.
The least
is.
Okay. As we can see, these are kind of deep waters. And this is not a space in which equal motions are even equally perceivable. So let's take several steps back and start by thinking about that. Okay, so back up. Here are the perceivability of different geometric distances in this chromaticity diagram. So the ellipse is an equally perceivable, they're called macadam ellipses, but you can just think of them as being a just noticeable difference. And the just noticeable differences are much bigger here than they are here. We're very sensitive to these colors here. So this is not a good space in which to do any transformation like that. We're going to move some colors a lot more than we're going to move others, and it might not be necessary to do that. So let's try to create a space where all the distances in the space are equally perceivable. So there are lots of spaces that have been proposed. They are typically nonlinear transformations of these linear spaces based on human perception. So here is one such nonlinear transformation, and all of those ellipses now become circles, and circles of the same size. So there are several of these spaces. Here's one of them, L star, A star, B star. So this is lightness, and A and B are color opponent pairs, which I'll talk about in a moment. You can think about this as being sort of in the reddish greenish and this sort of being in the bluish yellow, and here is the actual formulas. So in that formula, the x0, y0, and z0 are the coordinates of a reference white. So you have to choose a reference white. And then look at the powers there. That's kind of interesting. So what those powers are doing is they're effectively a gamma transform. We've talked about gamma transforms before. And when I talked about gamma transforms, I said, first I said, well, it's because the cameras used to do it. Or sorry, the displays used to do it, so the cameras have to do the opposite. And then later on I said, well, because of that curve that we have to do quantization very carefully. But I never really said what that curve is good for. It actually turns out to be very close to human perception, that we are sensitive to light in this same curve. And therefore, after you've applied that curve, it's a good space in which to do quantization. We'll talk about that again later when we talk about JPEG compression. Exactly what that power is turns out to depend on whether you're in a dark environment or a light environment. So dark living rooms versus offices might have a different curve, but it's a reasonable number anyway to use something like a third. Okay, let's talk about those opponent color thingies. So Leonardo and artists have talked for a long time about complementary colors. The fact that certain colors seem to clash with one another or make the whole thing appear to vibrate. They would describe it in a variety of different ways. And so Newton knew about this idea of complementary colors, and he tried to arrange those colors across the circle from one another. Because he had this notion of a circle, but he didn't have precise spacings for the colors along the circle. So he tried to get the complementary colors kind of roughly opposite. He did some other really strange stuff having to do with relationships to musical notes, which turns out, I think, not to be a relevant analogy. But the way the history of science goes, those mistakes that the famous scientists made are just kind of swept under the rug. But it's actually interesting to see them, because if we try to invent things new ourselves, we will make many of these mistakes as well. And so it's interesting to study the historical ones. So the Comte de Buffon observed that after-image colors were the same as complementary colors. So after-image is a psychophysical effect. I won't force this on you now, but you can go play with this on the slides later, stare at the dot in the middle for 30 seconds, then look at a white screen, and you should see the colors on the right. And those are the same colors that artists have always said are the complementary colors. Now, isn't that strange? Because this is not an artist choosing those colors. This is your human visual system just reacting. And so in the 19th century, in the history of psychophysics, one of the questions they wanted to answer is, why is this true, that the after-image colors seem to be the complementary colors? And what they came up with that is now accepted as correct is that there is processing in the retina that computes this. And so this is thought to be the bipolar cells in the retina, and that they will compute sums and differences of the colors and produce two different channels, a blue-yellow channel, a red-green channel, and a light-dark channel, which is just the sum of red and green. They don't bother with the blue because it doesn't add that much to luminance. And that's an opponent process coding of the three-dimensional color space. So we therefore have some basis in psychophysics to take advantage of that for color representations. And let me show you two. I'll show you television and I'll show you JPEG. The second one being slightly more relevant for photography. So for National Television Standards Committee television, their primaries are Y, I, and Q, where Y is just luminance, and then this axis and this axis are sort of these opponent process colors. And there's a matrix from an RGB. That matrix will depend on the particular RGB you've chosen. Here is the I and the Q space. So there's I, and vertical is Q. So these are just 3x3 matrix transformations. So I didn't really say this before when we were talking about the rho gamma beta space and the RGB space and the XYZ space. They're all just linear transformations of one another. So they're representable by 3x3 matrices. You can convert from one set of axes to another set of axes with a 3x3 matrix. So this doesn't particularly give the rho gamma beta, but you could also do that. That's just another matrix. So here's what the decomposition looks like into the luminance and the two color channels. And the way television works, turns out we're more sensitive to Y than we are to I and Q. And then within I and Q, we're more sensitive to I than we are to Q. This seems to be where the flesh tones lie, which is important for human evolution. And so this, in the radio transmission of television, I means in phase and Q means quadrature, and I'm not going to go into the electronics for it, but more bandwidth is devoted to the I than the Q. And more bandwidth is devoted to the Y than to both of those. And so there's a natural way in analog television to encode the relative sensitivity of the human visual system. Okay, let's talk about JPEG. That's a little bit more relevant for digital photography. So it's a similar system. It has a slightly different luminance, Y prime, CB and CR, and it is a slight rotation of those axes from I and Q, the 33-degree rotation. So it's a similar set of axes. And there's a little bit more going on here. If we look at this formula, the input are the original RGB that have been raised to a power, gamma. And so the gamma is the same gamma that we talked about before, or it might be the gamma for a particular color space, a standard color space. So the order is as follows then. You start with the RGB in some color space that comes out of your camera. Let's say it's sRGB. You then raise it to a gamma. You then plug it into this matrix, and you come up with Y prime, CB, and CR. That's what you would use in the JPEG encoding. There's one more step that the JPEG encoding does. It's noted that we're more sensitive to Y prime than we are to CB-CR, same as I said for television. And so what is often done is to reduce the spatial resolution of the samples of CB and CR. And so a typical one is called 420, written like this. And what it means is in practice is that there'll be, for every 2x2 block of pixels, there'll be a Y prime for each of these pixels, and then there'll be a single CB and a single CR for the entire 2x2 block. And that's what goes into the JPEG encoder. We'll come back and we'll talk about that again when we talk about JPEG encoding, because there's a lot more that JPEG does. But I want to show you the color space aspects of it now. Okay. So This is an orange tinted slide from my class at Stanford because it's getting a little bit esoteric. To define an RGB color space, then one needs the location of the RGB axes in this linear space. So it's 3 vectors that stick out in rho gamma beta space that could be non-physically realizable, like the XYZ, and the location of the reference point. And so sRGB defines the reference white as being this D6500 equivalent, and that sets the scaling of these hidden knobs that defines the RGB cube for sRGB. And then the particular, let's see, is sRGB up there? Yeah, there it is, right there, sRGB. Here's another one that you might have on your camera. Some cameras will allow you to switch to a different system, and then the RGB values that get spit out are different RGB values. The mapping might be linear, like the 3x3 matrices I showed, or they could be a nonlinear mapping. sRGB uses a nonlinear mapping because it's got that gamma transform in it. And that gamma transform helps the quantization that follows to well represent our relative sensitivity to different brightnesses. Okay, enough on the theory. Let's go back and solve this problem we've got. So we've still got his necktie out of gamut, but we now know that the right thing to do is some perceptually uniform space. So we take the sRGB or the XYZ that I got out of the lab, run it through this nonlinear mapping to produce something like L star, A star, B star. That should be a lowercase, I think. Then we perform some compression in that space. And then we perform the nonlinear mapping to go to some other space, like CMYK or RGB, depending on what we're doing. So there's that mapping there. So this reduction, called gamut mapping, might have several options on how it's done. And so the options, let's bring up Photoshop. And oh, I forgot a demo that I wanted to give earlier. Push the stack for a second. This is a nice demo. This is white balancing of a raw image of the cathedral in Cusco. And in the loader for the raw file, you can change the color temperature. So it's the same as changing the color temperature when you took the picture, except for quantization. So I can say, well, I actually thought that it was a tungsten light illuminating that scene. And then you can see what happens. Or no, I thought it was a northern blue light. And let's see, so maybe that's not true. Is the raw, it has not been, has it been multiplied?
There's very few cameras that do analog white balance.
No, in the DNG file that would be the input to this, has it been multiplied by, it has not. Okay, I'm sorry, I take that back, that's wrong, thank you for correcting me. So there's no quantization that's done, it is just the raw pixels off the sensor and a suggested color temperature.
So
Right.
So then, if you're shooting in RAW, then you basically don't have to care about.
That's right, if you're shooting raw, you don't have to care. You could do it just as easily here and there will be no loss whatsoever. So, sorry?
Potentially even easier, because I mean you can play with it.
If you'd like to curate all of your photos. So, even if we take the original color temperature, here's what I think is roughly a perpendicular. So Zalman, is this just a perpendicular to the color temperature curve? So you can think about this as the correlated color temperature thingy, which is roughly perpendicular, but not exactly. Or, so my tool for, oh, maybe I can reach it. Yes. Or I can say, I will choose a neutral object for you. And so I can go choose one. So if I choose this, that's not going to be a good idea. If I choose this, it's probably not a good idea. If I choose the cloud, though, that probably is a neutral object, right? And sure enough, it actually comes up with a reasonable white balance if I chose the cloud. Okay. Pop the stack. So we were talking about
Neutral doesn't mean white, it just means R equals G equals B.
It's the thing you want to be white in the photo.
the thing you want to be white, the thing you assume is reflecting all wavelengths equally, and the cloud's actually a pretty good guess for that.
Any gray
You have no idea how terrifying it is to give a lecture with Zalmanstern sitting in the audience. He was the tech lead for Adobe Camera Raw for 6 years. And I'm showing Adobe Camera Raw here. Just so you all realize this. All right.
It worked out. He got here eventually.
Oh, that's right. I can't show a Photoshop window. All right. I can fix this. I'm going to mirror displays, screw up the locations of all my windows. And here we are. And we don't need that. So let's look at two things. So first of all, if we want to print that photograph, so the printer dialog will allow me to say either the printer manages the colors or Photoshop manages the colors. And then it will also allow me to choose from among any one of several rendering intents on the gamut mapping. They don't have precise definitions. They have intents. We intend it to maintain certain relationships between colors, or we would like it to keep saturated colors as saturated as possible. And then it is up to the vendor, in this case Adobe, to decide how they would like to implement that compression. So these are not precise specifications. And then we can also, right, okay, so let's cancel that. Uh-oh.
Escape.
Thank you. So let's try something else. Let's try assigning a color profile, which should do the same thing. So assign a profile. And, oh, sorry, not assign profile, convert to profile. And so that will allow me to choose what color space, and let's do Japan Color 2002 newspaper. Watch what happens to Greg's shirt on the left. See that change? Now I can fiddle with that depending on what kind of gamut mapping I want to do. Well, I want to preserve more saturated colors or do something else. So all of the controls that I just talked about are here. By the way, there's not a mirror in the middle of these scenes. These are my twin brothers. They're twins. All right. Where is the mirror button? Oh, there it is. Okay. All right. So I have another demo I can show you, which is an applet that does the same thing. So this is a really fun applet to play with. Here it is. And so you can, first of all, you can choose the number of primaries you'd like. 4, 5. So each primary then, remember, is a vector that comes out of the origin and pierces through this chromaticity diagram. So we can choose the number of primaries. We can set a typical printer gamut. It's got those 6 points for the Neugebauer equations, or NTSC. Let me reset it. Reset. And now let's look at what the gamut transform looks like. So watch what happens to all the points that are outside of that triangle. That was the first one that I said, where it just took the points outside the gamut and ran them perpendicularly down. In this particular, remember, this is not specified. The rough intent is specified, and then vendors can do whatever they want. So in this case, the vendor was my teaching assistants for this course, and this is what we did.
Absolute colorimetric and relative colorimetric are typically going to do the same thing across any implementation now.
Okay.
They're pretty close. Other
The-
ones are completely out.
Yeah, Zalman is saying that typically these days the absolute colorimetric and relative colorimetric will do the same thing. They don't in our implementation. So here's the relative
So they
colorimetric.
don't do the same thing as each other. I'm just saying that those two, the spec for those things is not completely wide open.
Uh-huh.
The spec for perceptual and saturation is anything you want. I mean,
I see the spec for this is not as wide open as the spec for the other two, is what Zalman's saying. Yeah, sorry. All right, so you can go play with this yourself. You can kind of see the way it does the various compressions, but that might not be the same as what Adobe uses. Okay. All right. Yeah. Showed this nice demo. And I showed how you can do it explicitly in Photoshop. So color spaces and color management. So I'm not going to spend time on this except to point out it's getting better. It's getting a lot better. It isn't as much of a mess as it used to be. Canon cameras, Nikon cameras, they have a variety of color spaces. Printers now are cognizant of the color spaces. The desktop scanners, for some reason, seem to be the latest, but I think even now that they do the right thing as well. This is a few years ago. Apple has particularly good color management across all of its products. When I show something in Safari, I show it in Mac Preview, it'll be the right color. If I have a wide gamut monitor, it will compress the colors appropriately so it doesn't appear super saturated on that monitor. However, let's talk about Google. Chrome does not do the right thing in all cases. If you don't have the right kind of profile in the file, not just the bits that say sRGB, it will do the wrong thing. And the colors will vary. And moreover, the colors will vary between the thumbnail. And if you resize your image inside the slide viewer, it'll actually flip colors on you in real time. And Android is not color managed at all. And so this leaves it effectively up to the vendors what color things will appear by changing the display on their phone. And so if Samsung wants a particularly bright display in an Android phone, they just make a brighter OLED screen. And it's a mess. And there have been lots and lots of arguments. It's unfortunately kind of tied up in the business model here where these vendors do have control and they like that control. On my phone, which is the Nexus 6P, if you go into, I think it's developer options, you can switch from native, which this is an OLED screen, so it's got very saturated colors, organic LED screen. You can switch to an sRGB mode, and it will do a gamut compression using some rendering tint, I don't know which one, and will produce colors that will look closer to what an iPhone would look like. iPhone is color managed to sRGB. So it's still a bit of a mess there. All right, so talked about the chromaticity diagram and the gamut mapping, and then we talked about perceptually uniform spaces and rendering intents. Any questions here? I didn't go nearly as much into color management as one could. One could do several lectures or even more on color management. Is there a learning-based, from the Dory, is there a learning-based auto white balance algorithm implemented in a commercial system? Don't know the answer to that. I assume that the camera makers have large training data sets and that that's effectively a learning algorithm. It's a tag training set. And so they'll compute some image-based features, maybe histograms over regions, and then they'll look it up in their tag data set and decide what the white balance should be. You can do little reverse engineering tests if you like. Try turning your camera upside down and seeing if it recognizes a beach scene, or things like that. Cameras that don't have a gyro in them. But yes, they all use something. It's all proprietary.
The downside of not having camera management in Android is just that if you really care that a source image gets reproduced faithfully, you don't really have control over that. I mean, what is
Yeah, in Android, you have no control over the faithful reproduction of something. You do if you display it in Safari, and you do in Chrome if you display it in Chrome in certain contexts, or if you have an sRGB monitor. But monitors vary widely. This MacBook Air is actually slightly less than sRGB. And so you might want to do some other manipulation of the space. And it may depend what app you display it on inside a phone, an Android phone. And so if we're trying to decide, well, should we do slightly warmer faces or cooler faces when we're tuning a camera? It depends where it's going to be displayed. And so people end up tuning it for a particular phone that's going to be sold in a particular country. but it's being tuned by tuning the display or tuning the photography software to match the display. There's no standard color management. It's a zoo. And with that zoo, I think I'll end today. So we'll continue on Monday.